Next topic is degree of freedom. Okay. Uh, Yesterday's class we discussed the basics of mechanisms, where we discussed the definition for mechanism, then for machine, then some common basic terms like link, joint, pair, chain, etc. So hope you know all these things, and all these are details are there in your note. With that only you can continue with this lecture. In this lecture we will discuss what is called a degree of freedom. Okay, so first I will start define it, and then we will continue. So generally it is the minimum number of independent coordinates required to specify a motion completely. Okay, that is a general definition of degree of freedom. Then we have a more better definition, degree of freedom of a mechanism. It is defined as the number of input parameters which must be independently controlled in order to bring the mechanism into a useful engineering purpose. So this is the input parameters we are supposed to give to a mechanism to get an output or non-output. Okay, when it is a non-output, we can say it is useful. Okay, clear. That is a definition of degree of freedom in case of mechanism. Now I will show. Here we have our mechanism. So remember, this mechanism transmits motion, rotary motion to linear translation or vice versa. And this is called a slider crank mechanism. This is a very important mechanism. And why it is called slider crank? The rotating part in any engine is called crank. So we have a rotating part, that is 2, and sliding part is called slider. So that's why the name slider crank mechanism. So in this mechanism we discussed such that when we give a speed, give a rotation to this link 2, 4 will translate, right? That we know. So what we can say, this case degree of freedom will be 1, because we need only one input parameter, that is the speed of 2 is enough to determine the speed of 4. Otherwise, if you know the speed of 4, you will get the speed of 2. So here degree of freedom is 1. This is the meaning of degree of freedom. Then we will see in more details. Okay. And before we go further, there is one more point you have to note. That is a very important point in that you can put as a note, and that is when for a mechanism, when we count the number of links. Okay, when we count the number of links, all fixed links should be counted as 1, and a single link, all fixed links should be counted as 1. You should use the number 1 symbol to represent a fixed link, and all fixed links should be the same one only. Okay, that is single link only. So without an explanation you can understand that, because we have to the thing that fixed link should be considered as 1. As I told in the previous class, I think I told you, here we have this 2 is fixed here. Okay, and this is also a fixed thing. Okay, so this is your fixed link 1. Here one fixed link. Then here in the slider there is a guideway. The guideway is constructed such that that is fixed. So the symbol tells you this is fixed. So we have another fixed link. So both are represented as 1. So to understand, I told you can join this to here, then it become a single link, right? We can join like that because fixed link means there is no motion. Since there is no motion, whatever outside the mechanism moving parts we can consider as fixed link. That is another point, whether we can understand it. Okay, whatever outside the mechanism or the moving parts can be considered as a fixed link because the motion is 0. So this will give you, if anyone still have confusion, this will give you an understanding. Here someone fabricated a mechanism. I'm just showing to say how the fixed link calculation only. Okay, so here you can see this is your what rotating part, your 2 is in the form of a circular plate. This is your crank. Now we have the link 3, that is the connecting rod. Then we have link 4, you can see here a black one, that is the slider. And this is the gateway, that is already mentioned here. This is the gateway, and gateway is fixed. Now you see what is the fixed link in from crank or with the associated with the 2, this one. So this is fixed on this table top. What is the fixed link? Corresponds to slider. This guide is in turn is fixed with this clamp, and this clamp is again on the same table. Then I think you will now someone had confusion, that is already now you understood. Okay, this is, it means this fixed link is this table. So this is only one link. So this is applicable to any mechanism. Please note, when all calculation, fixed link should be considered as 1. So I'll continue to degree of freedom. So this is the definition of degree of freedom. Okay, you have to note down both definitions, at least this definition you have to note down, degree of freedom of a mechanism. And the point I mentioned also, you should note as in some box, or you put some box and you can write the same. So how will you calculate degree of freedom of a mechanism? You have something called a number synthesis that is we will use. So first that you have to consider a mechanism with n number of links, and please write it. Consider a mechanism with n number of links, capital N. Okay, then write, let P1 be the P1, capital P1 be the number of pairs with degree of freedom 1. Okay, P1 be the number of pairs with degree of freedom 1. Let P2 be the number of pairs with degree of freedom 2, and so on, such that you can write for write for P3 and P4. You can write finally P5. P5 is the number of pairs with the degree of freedom 5. Okay, so we are considering a mechanism with n number of links. Now how will you calculate the degree of freedom for this? This is the most general thing. Okay, so you are writing F is equal to degree of freedom. So you have to remember there are n links in a mechanism, and remember the definition of mechanism, there will be a fixed link. When we fix a link of kinematic chain only, it becomes mechanism. So fixed link is mandatory. So in any mechanism there will be fixed link, and that should be considered as one link. Therefore one link will not be movable. So the total movable links will be n minus 1. That is the first term. We have n minus 1 movable links, that you can note down. Movable links n minus 1. So you remember, you just imagine that each link can move without any constraints. So if each link can move without any constraint, how many directions possible? Total 6. That 3 translation and 3 rotation. So total 6 degree of freedom is possible when there is no constraints. So what we can say is that maximum possibility is 6 into n minus 1, because we are multiplying 6 into each of the movable link. So the maximum possibility is 6 into n minus 1. Now it is given that pair means links together, right? Now 2 links to connected together. So we have pairs with P1 is the pair with the degree of freedom 1. Clear? So it is given that P1 having only 1 degree of freedom. Then how many directions are restricted? The remaining 5. We know that without any restriction, without any constraint, we have 6 possible. Then only one is possible means 5 directions are restricted. Okay, so you have to write that restriction you have to reduce from the total. This is the total, so you have to reduce that total restriction related to P1. That will be 5P1. That's why it is given as minus 5P1. Then when we come to P2, that is a number degree of freedom with a pair with the degree of freedom 2. So 4 directions you have to remove. So 4P2, then again 3, 4, and finally when it comes to P5, only one direction is restricted. One motion is restricted. We can write it as 1 into P5. Now when you come to P6, just imagine when you come to P6, nothing is restricted, so it will be 0. 0 into P6, 0. That's why it's not here. So this is the expression, general expression for degree of freedom of a mechanism in space. Because we are considering all six possibilities, therefore it is a mechanism in space. Clear? So this you note down all these, and finally you note write this expression. After understanding only, you write this expression and put this in a box. Now our discussions are limited to planar mechanisms only. Okay, when we say a mechanism in plane, so considering a mechanism as a planar mechanism or plane, we can say only 3 directions instead of 6. That is 2 translation and 1 rotation. That is a case of 2-dimensional or planar mechanism. So when there are only 3 directions possible, how will you calculate the same thing? You can write it as F equal to, you calculate it by your own. We have only 3 directions possible. If you have n links, there will be n minus 1 movable links. So what we can write is n minus 1 into 3 minus, what you have to write? We have only 3 directions possible. Then if P1, if you take 2 directions are restricted, so you can write minus 2P1 minus 1P2 and so on. Then remaining will be 0. So the expression will be, what is the expression? Should get it in your book. Okay, 3 into n minus 1 minus 2P1 minus P2. That is a expression for planar mechanism. Put that expression also in box. You have to write it as for planar mechanism and write that in a box. And this expression is called Grubler's criteria. Okay, please note that also this expression for planar mechanism, this expression is called Grubler's criteria. Okay. Now you consider few diagrams, then how will you calculate degree of freedom? Okay, so first consider A. We have a mechanism, so our expression is 3 into n minus 1 2 P1 P2. So you should know n, P1 and P2. Here you count the number of links. Number of links is n. We have link 1, link 2, link 3 and link 4. So n equal to 4. You write it, n equal to 4. And these all are joins only. Okay, not other links. Don't think that it's a big circle. Don't think that it is another link. This is pin joins only. Now how many pairs we have? 1, 2, 3 and 4. 4 number of pairs. So we have P1 and P2. P2 means there are 2 degree of freedom. In none of these cases we have 2 degree of freedom, because you can see this is a 2 rods connected by a pin joint. There will be only 1 degree of freedom. 2 degree of freedom cases I will show in some coming slides. There will be 2 degree of freedom. Once you saw that, you will understand what is 2 degree of freedom. So in all these general cases we have only 1 degree of freedom. So all these 4 pairs are P1 only. So you write P1 equal to 4 and P2 equal to 0. Now you calculate what will be the degree of freedom. So 3 into 4 minus 1, 9, 9 minus 2 into 4, 8. So you should get it as 1. So the answer for A is 1. Okay, so you write it as determine the degree of freedom of the following. Then write draw this diagram, and below you write solve it. Write n, P1, P2, then write the expression and calculate and write the final answer. Okay. See, all these things should be there in your notebook. Okay, that's why I'm specifying all the again sometimes. Then next, we can go through. Okay, on this one also I'll show. Here you can see a shaded shaded thing, so that you have to understand that is a single link. Okay, when we have a shaded thing, that you have to understand it is a single link. Now you count the total number of links in case of P. So I will count here 1, 2, 3, 4. Then we have a triangular one 5, another triangular one 6. So number of links are 6. So you write it n equal to 6. Then you calculate the number of pairs. Pair 1, pair 2, 3, 4, 5, 6, 7. So you have 7 pairs, that is P1. P1 equal to 7, P2 equal to 0. So you will calculate how much number of links are 6. So 6 minus 1, 5, 15. 15 minus 7, 2. I think again it will be 1. Okay, that also you write. Then use do for C and D. Then consider E. Same method, use just count all the links, count all the pairs, substitute in the expression and find. In case of E, you see, so you remember this is a triangular shape, 3 links connected together. So this is an example for structure, you remember, right? Because there is no relative motion possible. So when that no motion possible, what should be the degree of freedom? That you have to think. Degree of freedom should be 0, right? Because it is locked. So you should get it 0. Now we can check the expression. So count the number of links 1, 2 and 3. Now count the number of pairs 1, 2 and 3. So you have 3 links, 3 pairs. So you put it in the expression F equal to 3 into n minus 1. You have 3 minus 1, 2, 6. 6 minus 2 into P1, 2 into 3, 6 will be 0. Okay. So the expression is verified. Okay. So like that you do for D and C. Then next, another definition. It's not a not very important, but you should know it. Okay, this definition. Write it: redundant degree of freedom. If one or more link can be moved without causing any motion to the rest of the links in the mechanism, then it is called there will be a redundant degree of freedom. Okay, so again read it. That is, there are a lot of links. That means we have a lot of joins and pairs. In some links, if the motion is not affecting the others, then that need not be considered in the calculation of degree of freedom. So it can be neglected. So that is called actually redundant degree of freedom, because redundant chain means there is no motion. So it is similar that redundant degree of freedom. I'll show the example, then you will understand. Now consider this one. We have a mechanism. You can see the fixed link 1. Then we have a link of circular plate, link 2. Then we have another circular disc, small one. We have 3. And we have a connecting rod like thing, that is link 4. Okay. In this case, imagine the motion when 2 rotates, 3 can also rotate, and 4 will also oscillate, right? As the 2, since the center of the rotation of 2 is not at the, is offset by some distance, therefore this will create a oscillation in 4. That was a change in position of 3. So oscillation in 4. Oscillation of 4. Clear the mechanism. So here there is a redundant degree of freedom. So which one you know? Because this 3, can consider this 3. See, this 3 can rotate. Right? This 3 can rotate without affecting the motion of 4 or 2. Is that correct? Just think. even if the 3 rotating by its own axis, that will not affect the oscillation of 4 or the rotation of 2. So in that case, that is a concept of redundant degree of freedom. So there will be a redundant degree of freedom. So how will you include this is, when the calculation of degree of freedom, you have to reduce this value. That means without considering the redundant degree of freedom, you will get a value for f. Then you have to consider this redundant degree of freedom such that the actual f value will be the f you obtained minus number of redundant degree of freedom. Here it will is 1. So f minus f, the obtained of minus 1, that will be your actual degree of freedom. That you have to remember. Okay. So you can take this as the explanation and also an example. You can draw this and find the degree of freedom of this. Okay. And you remember, you have to write the expression like this: f equal to 3 into n minus 1 minus 2p1 minus p2. You can add minus fr. You can write it as fr, that is a that can represent the redundant degree of freedom, or any letter you can give. So there you have to add the number of redundant degree of freedom. Usual mechanisms, we don't have such thing, so it will be 0, so you are not considering. But this is only rare cases we have this, then you have to consider that for the exact calculation. That's all. Okay. Then you have to do some questions. So I already mentioned how to count link and pair. So the questions are: first question, determine the number of binary links, ternary links, binary joins, ternary joins, and pairs and links. So you calculate each of them and write. How will you calculate? First, you have to calculate the binary links. So I told that the shaded areas representing one link. So you have a lot of triangular shaded areas. All these are single links only. These are ternary links only. Okay. Then binary links means you have 1, 2, 3, right? I think it will be 3. Similarly, ternary link means you have to calculate 1, 2, 3, 4, and 5. So you have 5 ternary link. Then you calculate binary join. Binary join means only 2 links are connected at a join. When 3 links are connected at a join, it is a ternary join. So is there any ternary join here? Consider this point. This point, you have a ternary link, we have a binary link, another binary link. So this will be a ternary joint. Like that you calculate. And the next question, calculate the degree of freedom of the following. So we have 3 questions. One is the same previous example. 3 questions, all these 3. Okay. And here what else? In the same diagram, I'll explain the P2. Okay, that's a thing we missed. So I told that degree of freedom 2, where we have a degree of freedom 2 pair. You consider the pair between 2 and 3. Okay, consider the pair between 2 and 3. So by specifying only the speed of 2, we cannot determine the complete motion of 3. So you know that it will be rotate, and this is not a fixed joint also. Okay, this point will change. At the next instant, both the point on the circumference will be changed because this can rotate. So in this case, with only one input, we cannot specify the complete motion. So we need 2 inputs. We have to specify separately only. So this is an example for degree of freedom 2, pair of degree of freedom 2. So this is also example for higher pair, we can remember, because this is a point contact or line contact. So usually higher pairs we have degree of freedom 2. Okay, that you can keep in mind. So you can solve these 3 questions. in your book. If you have any doubt, so I'll stop here. If you have any doubt in any of the things we discussed in this, you can ask. Okay, so this is a lecture actually for today's class. We didn't have a live class. Okay. Okay then, thank you.